Hello, ladies and gentlemen, and welcome back. Root Beer here, looking at question number 9 on our 2010 Euclid Math Contest. Now, question 9 here, they're being a bit sneaky because in A part we've got parts 1 and 2, and then we've got a B part, so this is really a 3-part question, although you can certainly expect that these parts in A should be related. Alright, what have we got? If theta is an angle whose measure is not an integer multiple of 90, just looking ahead, I guess that's to make sure that we don't get a 0 when we divide here. Prove that cotangent theta minus cotangent 2 theta is 1 over 2 theta. Alright, so it's an interesting little trig identity. Well, we'll start with one side of the expression, and we should be able to rearrange it to get the other side of the expression, 1 over 2 theta. It was both cotangents, no cosines, right? Okay, so cotangent, that's sort of an odd one to use. But we can remember that's cosine theta over sine theta. And then we'd have minus cos 2 theta over sine 2 theta. Well, at least there's a sine 2 theta right there. But there's a bit of an issue. I've got a fraction here, but no common denominator. So what can we do? Multiply top and bottom of that first expression by 2 cos theta. Because 2 cos theta sine theta, more often written 2 sine theta cos theta, is the same as 2 sine 2 theta. Okay, so I'll get 2 cos squareds up here. While we're at it, I'm going to take this opportunity to expand cos 2 theta, which also has an expression. Actually has several expressions, but I'm going to go with cos squared theta minus sine squared theta, just because that's the first one that pops into my head. And now, since we have the same common denominator, we get to say, oops, wrong thing there. We get to say sine 2 theta on the bottom. Now we just need to turn the top into 0. Or not 0, 1. Okay. Well, one of these cos thetas and one of these cos squared thetas are going to cancel. So we're left with cos squared theta here. Minus minus turns into a plus. So we get plus sine squared theta. And we can see by that Pythagorean identity, everything is going to work out. So we started with one side of the expression, got the other side. We're done. We don't really need to explain it as long as the steps are broken up and clear. However, if you're worried, and especially if you were, say, facing a similar question but with less straightforward trig identities, if you're worried, write down the trig identities, say this is a trig identity. If it's got a name, you give the name, like the Pythagorean identity or a double angle formula or a half angle formula. Those ones tend to be commonly known, but something like if you're someone who happens to have memorized something like the triple angle formulas or the quintuple angle formulas. I certainly know quintuple angle formula is not something in the marking room that people are very familiar with. So if you're going to use a result like that, you won't always, but if you are going to use a result like that, write it off on the side and say, this is what it is, this is a trig identity, I know this, and you're good to go. Okay? So, that gets us 1 in part A. Now, how about, what do we got here for 2? Ross, okay, starts with an angle of measure 8 degrees and doubles it 10 times until he obtains 8,192 degrees. Fair enough. I suppose he could reduce that and figure out what the actual measure of that angle is, but probably doesn't matter. He then adds up the reciprocals of the sines of these 11 angles. That is, okay, he just calculates this S value here. All of these, fine. Determine, without using a calculator, so that makes me unhappy, the measure of the acute angle theta so that S is 1 over sine, or sorry, not theta, alpha. S is 1 over sine alpha. Okay. Well, thankfully they gave us an identity up in A, so I'm willing to bet that we should be using that identity. Now, sine 8 degrees would be sine 2 times 4 degrees. So let's say S is 1 over sine 8 plus 1 over sine 16. I'm going to drop the degrees. I mean, you should probably write them all in, but 4096, and I'm not going to write all the terms out unless I really think I need to, but I think I see where they're trying to go with this. So this is sine 2 times 4, plus 1 over sine 2 times 8, yada yada yada, plus 1 over 2, or sine 2 times 2048, plus 1 over sine 2 times 4096. Okay, but now, and we should say something like by 1, this turns into cotangent 4 minus cotangent 8, and then plus cotangent, I keep writing cosine, probably because I'm not used to writing cotangent, cot 8 minus cot 16. And you can see these two are going to cancel out, and you're going to get the next two to cancel out. And so on all the way down the line, you'll get cotangent 2048 minus cotangent 4096. That'll cancel out with the one before it, and then plus cotangent 4096 minus cotangent 8192. And those two cancel out. Alright, so S is cotangent 4 minus cotangent 8192. Alright, and now what in the world can we do? We need this to equal 1 over sine alpha. It's 1 over sine alpha, not 1 over 2 sine alpha or anything like that, right? Okay. 1 over sine alpha. So, I mentioned this already, but 8,192 is kind of an annoying number. Now, just like tangent, cotangent is periodic, that is, it repeats with periods. So how long does it take till it starts repeating? In degrees, it'd be 180 degrees. So this really scary looking 8,192 is really, let's see, 8100 is 90 times 90, so it's 180 times 45. So it's 92 plus a multiple of 180, and that's really the best we can hope for. Okay, so cotangent 8192 is equal to cotangent 92. So at least we got some smaller numbers, I guess. Cotangent 4 minus cotangent 92. Alright. Now, just like at the start of the question, it's kind of weird to be using cotangents. I think I'd probably be much more comfortable with sines and cosines. I don't know any cotangent identities, really. So I'm going to change things around, and hopefully this will help out a little bit. Cos 92 and sine 92, I think those guys can be changed a little bit, right? Let's see, we imagine our unit circle. 92 degrees is just about up here. So that's what, 2 degrees in just past the 90. And so getting back to black, change colors like this. So the sine value and the cosine value, well, that would be the same as the sine value of 2 and the, oops, wrong color, and the cosine value of just plain old 2, right? So what can we see? Cos 2 is the same as sine 92. And sine 2 is the same as negative of cos 92 because, of course, this little yellow bit is pointing in the negative direction, whereas this is pointing in the positive direction. Alright, so at least we get rid of 92's. And then what do we have? We have cos 4, sine 4, minus... the sine 92 on the bottom turns into a cos 2. And the cos 92, we can change this to a plus, and then we get minus cos 92 turns into a sine 2. And then what do we got here? We've got cos 4, sine 4. Well, those are just well, it's the same sort of thing. We want plus sign, common denominator, right? I copied that right? Yeah, cos 2. So get a common denominator. Well, turn it into cos 4, and this is sine of 2 times 2. I guess I could write the top as cos of 2 times 2. But we want sine 2, and we want to change that cos 2 into a sine of 2 times 2. So we need to multiply by a 2 and a sine 2, and we'll multiply by a 2 and a sine 2 here. So that'll be cos squared 2 minus sine squared 2 plus 2 sine squared 2 all over sine 2 times 2, and I'm betting the top turns into 1 again. Yep, cos squared 2 plus these guys cancel out, plus sine squared 2 all over sine. I guess I can just simplify it to 4 now. 1 over sine 4. So what did we want? We wanted alpha, and alpha is equal to 4. Oops, cut myself off there. There we go. All right, that was weird. We don't usually get strict trig questions very often, but there we go. And that certainly took a little bit of thought there. I like that there was this telescoping part in A, or in A1. Certainly it was... Oh no, I guess that was in B. A1's over here. So there's telescoping part in the first little bit, and that leads us to 8,192, which is a weird number, so we simplify it. And then that sort of got into my head, oh, we could simplify 92, because frankly, it's a weird number as well. Especially because we're also on the hunt for an acute angle, they say. So we get a nice little alpha 4 there. Okay, so that was all just A part. What have we got for B here? In triangle ABC, BC is A, AC is... So we're just numbering based off the angle that we're opposite of. And we know that A is less than a half B plus C. Prove that angle BAC is less than a half less than the semi-sum of the other two angles. Okay. Well, so what do we got here? Big old triangle. We've got A, B, C, and so opposite is A, B, and C, and we know that A is less than a half B plus C. That's what they said, right? Less than a half B plus C, and we want to see the angle at A is less than a half the angle at B and C. So maybe color code it a little bit. The red angle is less than a half of the blue and the green angles. Okay, so we need to show angle A. I'm not going to use the B plus A plus C stuff. The BAC stuff. I'll just say use my own notation. Angle A has to be less than a half angle B plus a half angle C. It's basically the same expression. I don't know why they didn't just write it this way. I think it's a little cleaner to see what's going on there. Alright, so that holds. Let's be clear because we're writing things up. So the thing we want to show holds exactly when angle A is less than a half. Now, angle B and angle C, they make up the rest of it. So we can replace them with 180 minus angle A. And then this turns into 3 halves. The minus a half comes over to the other side. Angle A less than a half of 80. So we get 90. So multiply by 2, divide by 3 will be 60 degrees. So we need to show angle A is less than 60 degrees. Once we've done that, then this all works out. So, okay, that's nice. I don't know if that's going to lead somewhere necessarily better, but at least I have options. Now, think very carefully. What were we given in the question? We're just given... We're not even really given any numbers, but we are told about the sides. Told about the sides here. And so... Gotta find some way to use these sides, and specifically the angle here at A, and that makes me think cosine law. So by the cosine law, what do we have? A squared is, I don't like these squares here. So B squared plus C squared minus 2BC cosangle A. Okay. So I don't like the squares because we're just given a nice little linear expression. A is less than a half B plus C. I also don't like this cosine. Cosine A... So angle A is less than 60 degrees. How could that be interpreted if cosine of angle A... Bust out our unit circle again. So 60 degrees is about here. That's cosine is 1/2. So I guess we have to show cosine is bigger than 1/2. Yes. Alright, that's not so bad. So now I've got another condition I can show, and this one at least relates to the cosine law, which is getting me back towards the sides, and the sides are what they tell me about. So, should we get cosine all by itself? It's a little frustrating because... I guess we should write it the other way. We don't have a whole lot to go on in this question. This is basically, we're just proving a triangle property. We don't have any extra conditions, nothing else, like all the angles are acute or something like that, or one angle is twice another, or anything, or a range of values, or prime numbers, nothing. We just have a single condition, and it is up to us to rearrange and talk about it. So bring that over to the other side. So B squared plus C squared minus A squared over 2BC. So I need to show that that's bigger than a half. That's the goal. Get that to be bigger than a half. Multiply by 2BC on both sides. Bring the BC's over. So that'd be minus BC plus C has got to be greater than A squared. I'm starting to get close to something, I think. Now, we are told A is less than a half B plus C. So if I wanted to talk about A squared, I'd have it be less than a half 1/4 of B squared plus 2BC plus C squared. So, might say 4A squared is less than B squared plus 2BC plus C squared. A squared is certainly less than that, but What in the world can we do about a b squared? Okay. I feel like there's got to be some sort of trick or something. So we've got a minus BC here, but I can guarantee a plus 2BC over there. Don't have 4A, I've got regular A squared. If I can get this bottom statement, then we're done. But the question is, can I get that bottom statement? That's the trick. I don't think we have, we really don't have any other equalities or inequalities to work with. A part is not going to save us here at all. Okay. Is it possible we were a bit hasty with something? Well, let's ignore the condition that I need to show. And just talk about this expression here. Cos A. Maybe I should keep cos A in what I'm talking about. I'm not sure. I do know cos of angle A is always less than or equal to 1. Can that build up an inequality for me? Because then 2bc is greater than or equal to b squared plus c squared minus a squared. So I'll say something like, we know this by cosine law. We know that b squared plus c squared minus a squared over 2bc equals cos of angle A, which is always less than or equal to 1. So we can say b squared plus c squared minus a squared is less than or equal to 2bc. Swap the sides. B squared minus 2bc plus c squared less than or equal to a squared. I don't think that's going to help us exactly. Because all I've shown is b minus c is less than or equal to a, and I don't even think that, that's not helpful. That's just regular triangle inequality, although maybe the fact that we've got a triangle is something I need to be using. So what if we multiplied this by 4 to get 4a squared? So we'd have 4b squared minus 8bc plus 4c squared is less than or equal to 4a squared. Combine the two and maybe something will help, or maybe not combine the two. Because then I just get something in terms of B's and C's, and while that might be fine, remember the thing I was shooting for. I need to show that this expression needs to be greater than, not greater than or equal to, greater than, strictly greater than a half. So I definitely need to have an a squared hanging around, I think. So what if, so maybe we'll say something like this. Multiply by 3, and then you'll get 3b squared minus 6bc plus 3c squared is less than or equal to 3a squared. Multiply both sides by negative 1, and you'll get 6bc minus 3b squared minus 3c squared is greater than or equal to negative 3a squared. Now I've got two expressions. So I got b squared plus c squared plus 2bc. And that's greater than or equal to 4a squared. Right? That's what we just had. That's this line up here. Now if I weren't such an idiot and lined things up properly, there we go. We'll say 2bc plus b squared plus c squared. If I add them, then minus 2b squared minus 2c squared and 8bc, that's got to be greater than or equal to a. So then divide by 2. I've got my a squared, but at what cost? So I think I've lost a little bit of what's going on here. That's fine, that's fine. So I'll say this. Plus, what could we do? What could we do? I've got too many b squareds and c squareds, so let's keep a b squared and a c squared away. And then we've got two others. Now they're both squares though, so if I bring them to the other side, I can only it's going to necessarily be positive. So we'll put b squared minus c squared, and then we get a squared plus b squared plus c squared over here. I still have 8bc here, but this is necessarily greater than or equal to a squared, since b squared, c squared are always non-negative. And that's helpful, I think, or it was meant to be. I'm not sure if it actually was. Alright, let's do a little rough work. What do I want to show? I want to show b squared plus c squared minus a squared all over 2bc is greater than or equal to a half. What would this actually mean? Because this is cos angle A here. So that would be b squared plus c squared minus a squared has to be greater than or equal to bc. That's what we need, and so we need to show b squared plus c squared minus bc is greater than or equal to a squared. So I don't have that. I have that, I have that. What could we do? This is what I need. I've got something greater than or equal to a squared. The problem is the b's and the c's are not facing the right direction. They need to be positive b's and positive c's. So maybe I went backwards a little bit. Or maybe we could add on another square. And bump these up. If it just add on 3b squared and 3c squareds, that should do. But then I got this 8bc here that's causing me problems as well, and I don't like that. All right, I'm not satisfied with this work we've got going on here. Maybe the triangle inequality isn't the right thing. Although I do like this, I can add on squares freely bit. That's nice. So we'll see. Alright, so what can we say with certainty? I know that 4a squared is less than or equal to b squared plus 2bc plus c squared. That's definite. So I definitely have that. Okay, I'm shooting for something that looks like a squared is less than b squared plus c squared plus bc. Plus bc or minus bc? Minus bc. Minus bc. Okay, so I need to keep these b squareds and c squareds where they are, but I need to somehow introduce negative 3bc's to this process. Okay. So 4a squared, and what in the world could I do? Maybe I do need the triangle inequality. So what would we say? By triangle inequality, b is less than, or a is less than b plus c, so a squared is less than b squared plus 2bc plus c squared. I knew that. That one was fine. But we also have a squared is greater than b squared minus 2bc plus c squared. That was the other observation. Oh. Yeah. Okay. And I really wanted to do minus 3 of these a squareds. And that got me an a squared off on the side, which was good, because that's what I'm shooting for. But the problem was too many b squareds and c squareds sort of died to make that happen. So can I do some other linear combination of them? Well, if I could get 2a squared and less than b squared plus c squared minus 2bc, that would be okay. Don't have anything like that, so that's a bit of a shame. But this is what I'm looking for, is the statement that I've got tucked down here in the bottom corner. Okay. What if we did minus 2? So this turns into minus 2a squared is less than or equal to 4bc minus 2b squared minus 2c squared. Add that to my 4a squared is less than b squared plus 2bc plus c squared. And I'll be left with 2a squared less than 6bc minus b squared minus c squared. I don't think it's going to work because I'm not getting a minus bc anywhere. This is my problem. But I could add a b squared plus c squared to both, or a b squared minus c squared to both sides. Right? You can always add squares onto the big side of an inequality. It'll just make it bigger. So b minus c squared and that would get me let's add on two of the, I feel like I'm either absolutely wasting my time or I think I'm really dancing around the right thing. Alright, let's try and go. I think the minus 3 might have been good. I can't remember exactly why I abandoned it, and that's not a good sign. But we'll say 6bc minus 3b squared minus 3c squared, 4a squared less than, so when we add them, it'll definitely be a less than sign. Then I'll get a squared. We do 2bc plus b squared plus c squared. That'll be 8bc minus 2b squared minus 2c squared. I need to have b squareds and c squareds here. So that'll be less than or equal to 8bc minus 2b squared minus 2c squared plus 3 copies of b minus c squared? No, because that's exactly what this was. Alright, well, I keep trying to add the inequalities and it's not yielding exactly what I want. So, fresh ideas. If I can't add and subtract it out, and you know, maybe I haven't exhausted that, but maybe I can divide it out. So that's less than, what was it, b squared plus c squared. Was it plus 2bc? Was it plus or is it minus? Plus 2bc. Okay. Yeah, sure. Okay. If I want to divide it out, then I need to, if I want to just get the a squared on the one side, I need to divide by 4. I don't have 4s with my b squareds and my c squareds. But, as I've remarked a couple times now, we can always add on the right stuff. We can add on squares, so I could add on 3b squareds, I could add on 3c squareds. Now, it would leave me with 2bc's. I need to get a way to get minus bc's. So what if we used the 3 minus bc squared? That would get me, before I was using 3 to cancel out the 4 and turn it into a 1. Now I'm using 3 to, I guess, add on and make these 4s. 2bc, and it would be minus 3 times, so minus 6bc. So that would be 4b squared plus 4c squared minus 4, there it is. Spent too much time trying to add on, add inequalities. I should have just been adding on a square at the end the entire time. Okay, fine, fair enough. Dividing by 4, we get a squared is less than b squared plus c squared minus bc. And then rearranging this, you get b squared plus c squared minus a squared is greater than bc. And so divide by 2bc, which, you know, they're lengths, so it's not going to change the sign. And we've only been multiplying and dividing by positive numbers here, but this is cos of angle A. And we already mentioned that that means the same as angle A being less than 60, and that means that angle A is less than a half the sum of the other angles, which we will just squeeze in here just at the end. But there we go. Okay, so that was quite a stumbling block in the middle, but that was my fault. I was trying to add inequalities, which seemed like the natural thing to do at the time. I had two inequalities. They both had a's on the sides, just multiply and cancel out the right way, but it just wasn't working out the way I intended it to. And look how many times I used threes, and I was dancing around the whole issue, and I never got it. But there we go. That finishes off question number 9 on our 2010 Euclid. We have just one more question to go, and that will be question number 10. I will see you for that in the next video. Until then, take care.